I'm going to guess that you're here watching this and listening to my sultry voice because you're about to interview, or you just did interview and it went south, or maybe you were in a conversation with your colleagues and it was embarrassing. I'm sorry. Before this video, I'm going to assume that you're here for interviewing reasons. So I'm going to frame this video in the context of the most basic and therefore annoying interview questions, because that's likely what you're going to face. If you are one of those programmers that gets annoyed being asked questions in interviews about code, well, I would suggest you get over it because nothing is going to change, and other programmers are happily checking their ego to get one of the highest paying jobs in the world. All right, well, speaking of moving on, I'm going to start with one of the most annoying interview questions that I can imagine: detecting if an array has duplicates. If you're an experienced programmer and you're asked this question in an interview, take it as a sign of respect. Most chefs out there can't properly make an omelet, or scramble an egg for that matter.
Back to basics, you know that? What I want you two to do, just to confirm that we do know the basics, both at the same time, cook me an omelet.
An omelette is probably one of the first things you learn to cook at catering college.
I've never cooked an omelette before.
Oh, don't be stupid.
I haven't.
Okay, hopefully we can have things be a little more positive in our experience. Let's take a look at our question. Here, I have a simple array with 7 values, and as you can see, there are some duplicates that my interviewer wants me to remove. Now, if you sense a trap, well done. While this algorithm is simple to solve, it's difficult to solve well. We'll start with the obvious solution, which is a nested loop. As you can see, my outer loop steps through the array, and my inner loop goes over it again, checking to see if the current loop value exists at a different index. It's about as simple as you can get. All right, well, maybe characterizing this as a trap is a bit heavy-handed, but I'll bet your interviewer will want to know why you thought about this solution. They'll likely ask you about its complexity and if there's something that might have better time complexity. Now, if you don't know what I'm talking about, that is okay. You're in the right place because we're going to get into that now. It all comes down to how many operations we're performing before our algorithm can give us an answer. Here, I have 7 items in my array, and I have a nested loop which will loop that array. So that's 49 iterations because 7 times 7 is 49. I know you know this. But here's the thing. Being literal like this and reciting numbers to your interviewer isn't cool. So rather than do the math and say 49 operations, just give her an equation. Like this one. You know that 49 is 7 squared, so you replace that 7 with n and say, well, it's on the order of n squared. And hey, that's big O. Great, I hear you. So what? Why do you need to know this? The simple answer is because n-squared code can usually be rethought, and your interviewer is waiting to see if you know this. You squint your eyes and hope that the code just appears, and look at that, there it is. Tricky you. But why is this code better than our first solution? The simple answer is that there are no nested loops, which is a good thing. To find the length of an array only takes a single loop to count up all the elements. Creating a set also takes a single loop, and we know that sets must contain unique values, so if the lengths of the two don't match, there was a duplicate. Okay, well, all that is great, but our interviewer wants an answer, and you and I know it needs to be something mathy other than, hey, there's no nested loops, and we're tempted to say that, well, it's 2n, but there's no such thing as order 2n. There are no constants applied to n when discussing Big O. This trips up programmers all the time, and let's see if it's easier when you consider graphing the problem. On the x-axis, we have our inputs, or n, and on the y-axis, we have our operations, some bits of logic that our code performs other than loops. The green line is relatively straight, or linear, no curves, and the red line, our n-squared algorithm, is quadratic. These terms are often used when discussing algorithms as well. Now, if you're not a graph person, you can simply count the loops in a given routine. 2 nested loops is n squared. 3 would be n cubed, yuck. Only 1 loop? Well, that's just order n. What about no loops? Well, we're going to get to that in a bit. Our interviewer likes that we have reduced our complexity from quadratic to linear, in other words, order n squared to order n, and that we can talk about it clearly and that we understand what's going on. Well done. Let's get on to the next question. A good friend of mine was asked to write bubble sort from scratch in an interview a few years ago, and she has over a decade of experience as a developer, and I promise you that you use tools that she has built every single day. Rather than get upset about being asked this question, she took it as a sign of respect and realized that her interviewer just wanted to know if she could make an egg.
Is this really happening? He can't even boil a egg. Thing's still got feathers on it.
Okay, well, what you're looking at is the bubble sort algorithm. This is what my friend was asked to code. Now, if you don't know what bubble sort is or what we're even looking at, pause the video, go have a Google. This is something that you should know how to do. Here's the thing about this question. Bubble sort sucks in terms of scaling, but can you see why and can you say why? Once again, we need to consider the loops. If we're looping over our inputs, just a single loop, boom, we know it's order n right away. If we have a loop within a loop, boom times boom, then we know it's order n squared. But what's happening here? There's only one loop, or is there? The last line of our function checks a flag and then makes a recursive call. Recursion is still a loop. In fact, it can be the worst possible loop that you can code. Here we are indeed looping within a loop, so this is order n squared. Wait a minute, you say? Hang on. What if the list is already sorted? Then we would only loop once and exit. Wouldn't that make it order n? As my friends in New Zealand say, yeah, no, mate. The thing about Big O is that it's not concerned with the exact values of n, only n itself. There is another notation called Big Theta that is concerned with scaling with exact inputs, which is important too, but when discussing time complexity in general, using Big O, we think in worst case. All right, well, we shall not be tricked. We reply that no, bubble sort is a crappy algorithm that's always order n squared, but has an order n theta if the list is pre-sorted. Boom, you nailed that question. Well done. All right, on to our next interviewer. They want us to find the intersection of two arrays. In other words, the values that the arrays have in common. We know that we could probably do another loop within a loop thing, which is called brute force, that is typically quadratic, or order n squared, looping over one list and then looping over the list again to inspect it, and so on. We know our interviewer wants something better. Having studied up on interview questions, we know we can use the hash table trick to bring our complexity down. We're not exactly proud of this code in terms of aesthetics, but we are proud of the complexity. Can you see why? And can you tell why this code, which does the same thing as our previous code, is order n or linear instead of order n squared or quadratic as my previous example? The answer is that we're using hash tables to optimize this routine, which you can think of as simple objects in JavaScript. If you don't know what a hash table is, key value pairs. Looking things up in a hash table is what's called order 1, the simplest possible thing you can do. The complexity of this algorithm is tricky, and this aspect of Big O can confuse a lot of people, and I mentioned this before. We're looping 3 total times in our code. How is that still order n? Do you remember the answer I gave you before? There are no constants in Big O. What we care about is the curve or the graph. As long as we don't have loops within a loop, we're good, and it just doesn't matter how many times we loop. All right, well, if you don't believe me, let's look at this on a chart. We have 3 loops inside of our algorithm, and that means when n is 2, we have 6 total operations. When n is 4, we have 12. When n is 6, we have 18. When it's 8, we have 24, and so on. You get the idea. There is no curve here. This is a straight line. It's linear, and that means it's order n. To make this algorithm order n, I had to avoid an inner loop, which would have made it order n squared. Instead, I used a hash table. This is the hash table trick, if you will, and I could have used a set as well if I wanted to. Anyway, it has a lookup operation that doesn't involve any loops at all. It's a key value pair, so if I know the key, I get the value immediately, and this is what's called constant time, or order 1. Here comes another graph. Aren't you excited? No matter what the value of n is, our hash table lookup will only require one operation, accessing the value by the key. This gives us a flat or constant complexity. Putting an order 1 operation in a loop is effectively multiplying by 1, and that is very efficient. That means it doesn't affect the overall math of our algorithm. Our interviewer is stoked that we could recognize a better way to do this algorithm other than n squared, and that we thought it through and were able to explain it. Well done, good job. All right, well, our last interviewer wants us to use our sorting algorithm to create a search routine. This is another super simple question and super annoying. But this one we know about, though, because we subscribe to Connery's YouTube channel, and better yet, we have also read his book, so we know all about this. So let's rock it. We do, in fact, know how to answer this question, but we want to show that we know other ways, good and bad, and most importantly, why our chosen solution is better. This right here is what's called a brute force algorithm that simply searches over the entire array, returning the first matching value. Now, I doubt many people would do something like this, but we're showing it here because we want our interviewer to know that we know the difference. What you're seeing here is called binary search. and it's the canonical example of an algorithmic approach called divide and conquer. That's an algorithm that does something by splitting things in half repeatedly. This type of complexity is logarithmic, or what we call log n, and is foundational when it comes to optimizing things. Logarithms are inverse to exponents, which means that the higher the value for n, the lower our curve gets. You can see the jump from log 2 of 1, which is 0, to log 2 of 10, which is 3.3. As n grows, however, the curve flattens, which is where the power of divide and conquer, which is always logarithmic, comes in. And divide and conquer can be confusing, so let's play with it visually. Here's a range of emotions that you might have at a party, sorted from sad to mad. I know, whatever, just go with it. Let's say we want to find the emoji in here that's the simple smiling one. Why not? We can stay positive. The first thing we need to do is to split our list in half. And we can do this because we know the length of the list, it's an array, and we can just divide it right in two. The next step is to look at the value in the middle, or as close as you can come to it, and decide if the value is greater or less than the value that we're looking for. Now, Party Kid looks much happier than our simple smile, so we know we can cut Party Kid and all of his friends to the right. Now we do the exact same thing with remaining friends. And by the way, if you can't cut in half exactly, well, you just do the best you can. Just pick one. Here we see our sad little guy. He's sadder than our smiley target, so we can cut him and all of the values to the left. All right, well, there's only 2 left, and we have to split right down the middle again, and we look left, and hey, look at that. We found our smiley friend, which only took 3 total splits, or operations and evaluations. Looking at our graphs once again, this makes perfect sense, because log base 2 of 10 is 3.3. We just had 3 splits, or maybe 4 depending. So you can think of this when you see 3.3 as well, it could be 3 or it could be 4. This right here is exactly how database indexes work. Here, I have 1 million users in my sample database, and Postgres is telling me that I'm able to use the index that I created to find a user by email. Now that makes us feel happy, but how happy should we feel? To find out, let's piss off our DBA and drop that index. You can see that Postgres needs to perform what's called a sequential scan. Can we explain that in a better way, you think? A sequential scan means that Postgres needs to loop every single row applying our filter. Loop every row. If you said order n, that is correct. We have 1 loop, we're looping every single row. Now right there at the bottom, note the execution time, 114 milliseconds. That's pretty fast. But if you load that up and do 1,000 of those queries a second, you're in trouble. All right, well, we put our index back because we want to keep our job, and now we're doing an index scan. Now, if you didn't know, an index is simply a sorted list of values, depending, of course, on what you're indexing, that the database maintains for you. Here we've indexed on the email address, which means that Postgres can use this email address and a variant of binary search in the background, which means that we are now log n. Note the execution time, by the way, 0.065 milliseconds, over 1 million rows. Now that is fast. We can go a step further and know exactly what our performance gain is. Instead of performing potentially 1 million operations trying to find an email address, we only need to perform 20. And once again, in reality, we could be trying to find the very first record and only run 1 operation, but Big O doesn't care about that. Big Theta does. And sometimes that's important, but in general, we think in worst case. Well, that's it for me. If you've learned something, please consider heading over to bigmachine.io to support my efforts. I dig into lots of topics just like these, but in a lot more depth. Thanks for watching. I'll see you again soon.